Robby.
Right. Thanks a lot, Bengsin. Yes, today I will talk about this topic of night images. So what kind of information that we can extract or enhance. Okay, so we know that this image is taken in the nighttime, and we know that the problem of nighttime is low light. And this is actually the well-known problem in this topic. Low light can hinder us, for example, from getting information in this region here, or many regions actually in this image. And maybe some of you think that, okay, so if we have this kind of low light image, why don't we just boost, right? By multiplying the pixels with some constant value. So if we boost, actually, this is what we will get. One thing that we obviously observe here is that the pixels become very noisy. And this noise problem is actually the core problem in low light. Low light is not just low light. Of course, low light means that there is no information, not much light coming to our camera, but also noise problem. And the interesting things about noise is that in some cases, noise is obviously can be differentiated from real signals or real structure. So for example, in this part of the region, we know that this is most of the cases can be due to the noise. But the part of here, for example, some of the signals is really not noise, they are structure, real structure. Right? So not the problem is how we can differentiate between noise and structure in this particular region. And of course, we can see here there's a lot of noise as well here, but this one is relatively easier because there is not much structure in the region. Okay, so aside from low light, actually, if we pay attention in the night images, we also have this glare or glow problem, or we call sometimes we can have float lights as well. So the problem here is that, of course, this region here, right, because of the glare, we cannot see clearly what is behind this glare here. And if we can, we actually want to remove this glare and find the information behind the glare. That is something that we want to have here to extract in more information. And also we have this kind of effects or light effects, right? So, and this is something that not really, in terms of the information, not really annoying because we still can see the object, but in terms of the quality of the image, it can also a bit something that we don't want sometimes. Okay, aside from this, we also have the problem of glow. Glow is something that you can see here that we have a light source, and then there is some particles, atmospheric particles, and this atmospheric particle will scatter the light, and then we can have these effects of glow. And aside from glow, we also have this called uneven light distribution. In some region, we have very bright light, but in the other region here, for example, we have very low light. And here we also have quite low light. So this is another problem in nighttime, that the distribution of the light is not equal or not uniform, not as uniform as in the daytime. Another problem in nighttime is light colors. In daytime, the light colors is dominated by the skylight and sunlight. But in nighttime, because there is no dominant light, and people actually have these man-made lights, and man-made lights can be varies in terms of the colors, then we can have this kind of effect. Some of this is bluish or whitish, and other parts here is reddish or yellowish. And this create complexity in night images. Okay, so this is some of the problems that I can mention here. Now, given this degraded night images, how we can enhance, how can we possibly enhance these images? All right, so one of the problems that we want to tackle in this in this line of work is low light. We want to boost the light, and not only just boosting the light, but we also want to keep the color. Sometimes when we boost the light because of the CRF, because of the camera response function, which is not linear, camera response function normally will be curvy. And because of that, if we just boost with multiplying the pixels values with a constant, then what we have will be a color that is different from the original color. For example, if we boost this region here, for example, it still looks green, but the greenness of this pixel will be different from the greenness when it is naturally light, something like this. So this is naturally lit, so we know that it's green. But if we boost this area here, the greenness will be different because of the non-linearity of the CRF or camera response function or gamma function. And that's something that we want to take care here. When we boost the intensity, we want to keep the color. Means that we have to estimate the CRF function. That's one thing. That's something that we want to achieve here. The second thing is that at the same time, we know that night is not just low light. Night images is also about glare, glow, and flood light. And that means that we cannot just simply boost the image. We also at the same time suppress this kind of light effects. We have to remove the color, reddish color. We have to remove the glare here, right? And that's something that becomes contradictory here because the problem now becomes that we want to boost the low light region, but at the same time, we also want to suppress glare and noise, right? Because if we just boost the low light, because if we want to just boost the light, the pixels values, then the glare and noise will be enhanced as well. And we don't want that. That's the problem that we want to solve in this particular work. And to solve this, we propose, it is actually published just in the main conference in this year, that we have a pipeline here. First thing in the pipeline is that we want to estimate CRF. And estimating CRF here means that we have one input image, and then we estimate the gamma function. And then once we have the gamma function or CRF, we linearize the image and then get the predicted linearized image. Okay, so it is to make sure that the color is kept properly when we boost the light. And the second module in the pipeline is that after we have the linearized image, we split this image into low frequency and high frequency. And in the low frequency, we notice that first is the high frequency. In the high frequency, we notice that all the noise and the structure, the edges, the boundaries will be here. And that means that we have to suppress noise in this channel here, in the high frequency image or layer. And we also notice that in the low frequency, noise is not dominant. And that's how, but the glow or glare will be dominant here in the low frequency. So in the low frequency, what we do is that we have to do some declaring or deglowing, and at the same time we want to boost the intensity. So after we remove the glow and the glare in this module, in the low frequency, in the HDR, we boost the low frequency layer. And once we have boosted low frequency layers, means that the low light become boosted as well. Then we combine the low frequency and the high frequency again, and then become our output. So this is the basic pipeline that we have here to deal with the problem. All right, so we propose a few losses. This is a semi-supervised approach. So we have a supervised training, and in supervised training that is particularly necessary for this CRF estimation, because we need to train this network here. And what we do in training this module here is that we take this separate from the other in the supervised training, and then just do in a supervised way. Means that we have the ground truth of the gamma function. And for that one, we model the gamma function with this parameterized model. This is like a PCA kind of basis function kind of model. And we have 11 bases for this one, and this one is G0 is the mean of the gamma function. Okay, so basically this one is just a normal supervised method. We have the ground truth of the gamma function, and then this is our estimation, and then this is the error that we propagate to the network. And the second loss functions that we have is that the linearized loss. So this one is image linearization loss, means that Z here, Z prime, is actually the input image, right? And if we do the inverse of the gamma function, so this is basically the inverse of the gamma function, it becomes linearized. So the same as here, if we have the input image Z prime, then using the gamma function, we can also have the linearized image. So then this is become our image linearization loss. So basically there are two losses here, which is a gamma function loss, and here is the predicted linearized image loss. So there's two losses there for the supervised offline training. And for the SDR, so the SDR module here, again, this is unnecessary. The SDR is needed because, as I mentioned, that in some region, the light is very low because the distribution of the light is not uniform, right, in one input image. So one of the region is low, but the other region is very bright. And if we just boost this one without SDR, for example, for the low light, the bright light will be saturated, will go beyond 255. So we don't want this to be clipped or to be saturated. And that's why we need to have HDR, so then everything can go beyond 255. Right? So, and that's the reason that we need to have this module, HDR module as well, to handle the problem. So that's the case. So first, we need to do the decomposition, and the decomposition is also network-based using this existing method, fast end-to-end trainable guided filters. And once we have the high frequency and low frequency, we boost it or declare the low light image and suppress the noise in the high frequency layers. And for the HDR loss, this is the X here is the output that we expect to have. And this is X ground truth, means that we have the HDR version, right? And we apply this loss. Applying this loss is the reason is quite straightforward, because X here image X can have a very high and very low intensity. And we don't want to have a loss that is dominated by the high pixels values. Right? So we want to have the low pixel values also play some role in this loss. So then we suppress the high pixel values by having this nonlinear transformation using log. And once we have this, we do this training on the module of the HDR module, and then that's the things. And X here again is the combination of the high frequency and low frequency after the processing of the suppression of the glow and suppression of the noise. All right, so yeah, so after we have this trainable supervised training, we move to unsupervised test time training, or this one can be done during the training, but also can be done during the test time training as well. So in this case, we have the CRF monotonicity loss, means because we don't have the ground truth now for the CRF, then we have put a constraint that the gamma function has to be monotonously increasing. So the gamma function cannot go down in the higher intensity. And we also have the CRF pixel linearization laws, and this one is expressed a bit complex in terms of the mathematics, but the idea is very simple, that in RGB space, the distribution of a patch in this RGB space have to be linear. Right? So that's basically expressed in this linear function on the top. So basically this one is imposing that the output after the linearization have to be linear in RGB space. And E here is the patches. So we have to collect random patches from the image, and S is the resolution of the patch. So we calculate this one for every patch in the image to make sure that all of them are linearized. And this one can be done during the test time. Right, so I give you the example of the low light suppression. This is the input, and this is the low frequency map that we have. And then after the suppression, we remove the glare, and we have to reduce the color effects. And then after we have high frequency, we combine with the high frequency again, and this is our output. So basically, this is the input that we have. This is the output that our module can give to us. This is another example. This is just low light, basically. This is the low light image, and this one is our output, and this is the ground truth. Okay, and this is comparisons with other methods, HDR, CNN, and single HDR, and this is all the state of the art. And as you can see, hopefully you can see that the color, for example, are quite maintained here. Unlike the RPMO here, the color are actually quite different from the ground truth. The same as the HDR, CNN here. So that's the advantage of our method. And this is another example, comparisons with line, for example. Line is a well-known boosting method, but as you can see here, it cannot maintain the naturalness of the color, right? Because it doesn't care about the camera response function. The same as other methods that exist in the literature. So about the boost, about the glare here, for example, right? This is a bit of glare here in the input image, but if you use line, the glare will be enhanced. But our method can suppress the glare, but at the same time boost the low light region here. And this is another result from other methods of low light image enhancement, because they don't really pay attention on the glare, so they boosted glare as well. So unlike our method here. Okay, so this is another example. You can look at the papers in our paper for the details of all this comparison. Okay, so, and this is, I will quickly explain about our other works, which is called night to day image translation for high level vision or higher level vision. Okay, so image night day translation is part of photo editing. Then it is quite interesting to have this kind of topics in our work. And also many mid-level or high-level data sets have no annotation for night images. Right? And this include object detection, depth estimation, and optical flow. So if you don't have the ground truth, how we can train the network? So that's a big question here for this high-level or mid-level data set for nighttime. And the problem is that the night image rendering, sometimes if we don't have data set or ground truth, we can do the rendering, do the synthesizing of the data. But nighttime image rendering that can capture real night effects like glow, glare, and even light distribution and so on is computationally expensive. It's intractable to render night images. So our solution is that because the daytime we have many annotation for object detection or depth estimation, we want to translate the nighttime data to daytime. So then we can utilize daytime annotation to do the job. Right? And the question here is then again, having having pair night day, so we know that we understand now that the translation for night to day is important for many different applications. But the problem is that how we can translate it properly, right? Because pair night day images is also not available. It's also intractable to find, but particularly in dynamic scenes, right? And unpaired image translation, which is used a lot in this current days, relies on unpaired GANs. So we have to use unpaired GAN, means that the nighttime and daytime, there's no, the scenes are different, but we have to use them because we don't have the paired GANs or paired images. So, and we know that unpaired GANs generate hallucination or fake content. And this fake content is bad for the high-level vision or mid-level vision. So this is the main problem of unpaired GANs. If you use an unpaired GANs, you will have this hallucination effects or fake content effect. And this is the problem that we want to tackle in this work. Not entirely, because it's still an open problem, but we make an attempt here. So anyway, so this is unsupervised nighttime depth estimation. So the application is a depth estimation here in particular, but it can be used for flow. We show in our paper that it can be used for flow estimation. It can be used also for object detection in nighttime, even though you don't have a bounding box for the night images. Okay, so anyway, so this one, we translate day to night. First, we train the network in the first stage. We have the day images, so with this day pair images, stereo images. And then we do the translation in the night images. Okay, so we don't have correct initialization, of course, for this. We don't have any pre-trained network for this. We just use random initialization for this network in the beginning. And then we translate this, assume that we can have somehow night images here, and then we can do the cycle GAN kind of idea to translate this night image to day image. So this is like a cycle GAN, which is also used in 2D GAN. So based on this, actually we can render this kind of day and night. The thing is that the new things here is that we add this stereo depth estimation here and stereo depth estimation here. And we assume that this stereo can be pre-trained using daytime stereo data that has plenty of ground truth. So then we can have the estimation here, and we assume that this estimation is somehow correct. It has become our upper bound. So we don't really need to backpropagate this one anymore, and we freeze this network because we assume this network is proper network. The problem is this network here, because the image for the rendered nighttime is not, in the beginning especially, is not properly done. It's not correctly rendered, especially for the intended object like this car, for example. Right? So in this case, we create another network, which is a depth network, the same as this network. They are not twin, they are separate network, but they share the same architecture. And once we have this input and then we put into stereo, we can have this depth estimation. And then we make a stereo consistency, which is very common in unsupervised learning. And based on this stereo consistency, we train this network here. So that's the process in the day to night. And we see the advantage of this stereo constraint because it will constrain the rendered nighttime as well. We will show that later on, the advantage of this stereo constraint or high-level constraint in this translation. The second stage is day to night, night to day. So we have the input nighttime. We don't have the ground truth of the depth. We only have this nighttime. We do the same thing. We render the day pair, and then we generate the night image. So for the day, we know that these are frozen because it's assumed to be correct. And then we have this the depth, and then again for the nighttime, although we have the input original nighttime, we actually don't use this. Why? Because SN here, the stereo depth estimation, it already get used to with the rendered nighttime. It's not get used to with input original image, because these two are quite different. Although they look the same, they are quite different. The noise level, for example, in the original input is much higher than the rendered night image. So this SN is not used to process the noisy input, original input image. So we use the rendered night images to be processed to get the depth using SN here. Now, that's the whole pipeline that we have, and it works. But the problem is that, as I mentioned again, that will be some fakeness or hallucination. So this is something that we will observe because in the daytime, the original nighttime here is actually glow. So this is glow and glare actually. But because in the daytime there is no glow or there is no glare, so what the render or the network will generate for us is this kind of three kind of hallucination or three fake content. Okay, so this is the main problem because the depth will be influenced by this translated image. And as I mentioned again, this is the input, the original input. As you can see here is actually glare, but the rendered image become three, and we have to deal with this, right? Because we don't want to have a fake depth. So what we do is that we impose structure preservation. So basically, this is our contribution here. We have a structure preservation between the input and the rendered image. What is the structure preservation? Structure preservation is quite simple. We have VGG here, and then we know that VGG is robust in the night. For object classification, is robust in the nighttime. Why is robust? Because in the first layers, VGG only focus on the edges and corners, and then we utilize these earlier layers for the structure preservation. And because we know that these earlier layers is much independent from the light. And this is our loss function here. Basically, phi here is the layer in the VGG. And this one is the input from the daytime. And this one is the rendered input, C, and X is the input. So we compare them. So, and we make sure that the content, the semantic content of this rendered image is the same as the input. And this is our results. We can successfully remove the fakeness or hallucination of this tree here because of the glare. Okay, so that's one of our novelty. The second is that we notice that if you have a very low light image like this, the boosted version, although we don't really use the boosted version because it's very noisy, you can see that this region here, although we know that it's a building, but it's actually very difficult to observe it because human can extrapolate our knowledge that it's a building, but actually there is no data there because the region here is very low in terms of the intensity. And that's why the generated daytime there's a hole because this is basically, there's no data. There's no light coming to our camera. So this is another kind of hallucination that we have to tackle because this will influence the depth estimation that we will have. So the idea is quite simple, that we put a smoothness constraint in this work. This is our smoothness, this is our contribution that we have this weighted smoothness. What is weighted smoothness? Is basically that we generate this weight map. The weight map is very simple. It is based on the intensity. If the intensity is high, the weight is low. If the intensity is very low, the weight will be high. So we put more weights on the low light, and then we smooth this area here. We smooth the area where the weight is high, means that the intensity is low. And this is how we define our smoothness using gradients, simple gradients. And then we impose this during the training, and it works. So the whole here now it becomes con. It's like a smoothness constraint in the depth estimation, basically. So okay, so this is when before we apply our loss. So you see that the glare or glow here become 3 if you use a normal cycle GAN or 2-day GAN. And if you apply this one, the low light here, it's become very holes here and holes here as well, right? And actually the results of the depth will be influenced by this. So this is actually, there's nothing like this kind of depth, but because it's assumed to be 3, then it will be influenced. It will give some influence on the output of the depth. Okay, so now if we apply our losses, this is the original input image. This is the sorry, this one is the original input image. These two. We look here first. This one is the one that generates 3, a fake 3. But now using our loss, it's kept to be like a pole here. Of course, we cannot have the glow because daytime there is no glow, right? And we cannot assume that this is to be a light here because the information is actually not there. There's a saturated pixels. And this one, the area here now become fill up, smooth. It's different from what we have here. There's a hole here and there's a 3 here. Okay, so now this is the depth estimation. Now you see that there is no structure in the depth, and this is become smooth. And this is the comparison with the reference day. It is not a paired image. Again, this is another image. As you can see, the cars are different, but the buildings are the same. And as you can see, there is not much thickness in our rendered images, unlike original cycle GAN or 2D GAN. Okay, so another advantage compared to cycle GAN is that if you just use cycle GAN without the constraint of our stereo, you see that there are a lot of hallucination. For example, people here not look like a people. They don't really look like humans, right? But if we impose this a high level constraint, you can have a better translation. So this is another contribution that we can make here, that using high level vision is useful. And I'm not really sure if this is important, but at least our studies show that this is useful. And I think this is something important as well, perhaps to explore further, how the combination of low-level vision and high-level vision play role to each other. And people don't really much explore this. That when they do the low-level vision, they just do low-level. When they do the high-level, they just do high-level. But maybe in the future, we have to combine to make these two high-level and low-level techniques strengthen each other. Okay, so this is another result that we have, but you can look at the details of this in our paper. This is published in 3DV, although we have the archive back in 2019 already. Okay, so yeah, so this is our publication, and thank you.
Yes, thank you, Robby. So we can ask maybe 1 or 2 questions here, and we can move to our panel discussion. So are there any questions to Robby's work and presentation?
There is a question in the chat. Where do the ground truths for the camera response function loss come from?
Oh, yes, there are. Okay, so I will show the. Okay, so for our CRF, the ground truth is actually, you know, some companies release their CRF, the camera function. Some camera manufacturers, and people actually gather this information and they put this online. So there is a data set already for this CRF, and we use this data set for our work. And they provide the images as well. Okay, any other questions?
There's another question. Up to what depth does the rendered day stereo pair maintain details?
Right, so this is a interesting question. So to be honest, we do not know. We do not know how much the details that we can extract in this depth. What we know is that we just follow whatever the state of the art of the depth estimation. If the depth estimation here can go up to very far, for example, because this is something to do with the epipolar geometry. So if it is very far, the disparity will be very low. But if the method can capture this disparity, small disparity, and then compute the depth, then we can have that. Of course, this also depends on the length of the baseline, length of the camera 1 and camera 2 in the stereo. If the camera is very close to, for example, then the disparity for a certain distance will be gone. But if the baseline is very far, then it will go further. So this is based on the configuration of this camera, but also depends on the method itself. And we just use a state of the art of the stereo.